Hi everyone, I am Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about crystal structures and few basic definitions that are involved with crystal structures. So let us see the topics for discussion today. We will discuss about in the introduction to crystal structures, then what a space lattice is, basis, unit cell, and the lattice parameters that are involved with crystal structures. Now coming to why we have to understand about crystal structure. The reason is any solid you take, it consists of a number of atoms or clusters of atoms that are arranged in close proximity, and the behavior of the solids in their mechanical, metallurgical, electrical, magnetic and optical properties are very closely related to the scheme of arrangement of atoms. And if we understand the arrangement of atoms in a crystal, we can very clearly understand the properties of solids. That is why it is very important to study about crystal structures. Now, coming to the basic of arrangement of atoms and molecules. So based on this arrangement, this material solids can be classified into different categories. The first classification, if we see, is amorphous solids and crystalline solids. So if you take solids, either they are amorphous or crystalline. We will see in detail about amorphous and crystalline solids in the next few slides. And coming to crystalline solids, they can be classified as covalent solids, metallic solids, ionic solids and molecular solids. And then in covalent, we also have 2 dimensions and 3 dimension solids. And in molecular solids, we have polar, non-polar and hydrogen bonded solids. So now, when it comes to non-crystalline or amorphous, non-crystalline solids or amorphous solids, the arrangement of atoms in 3 dimensions is random. Then we call them as non-crystalline or amorphous. If the arrangement of atoms in a crystal structure is not in an orderly manner, it is in a random fashion, then we call it as amorphous solid. And these amorphous solids, they do not have directional properties. Therefore, we call them as isotropic substances. And also, they do not possess any regular shape and they have a wide range of melting points. When it comes to melting points, we see a particular substance melting when it is heated to a certain temperature. But when it comes to amorphous solids, they do not have a definite melting point. Best examples for amorphous solids are glass and rubber. Now coming to crystalline materials. In crystalline materials or crystalline solids, there is periodic arrangement of atoms in all the 3 dimensions. Wherever there is a periodic arrangement of atoms. Periodic, when we say, it is in a regular fashion, which repeats after regular intervals of time. And it has a regular shape. And when we take a crystalline solid and break it into pieces, all the pieces will have the same regular shape. That is the most important property of this crystalline substance. Also, it has a sharp melting point. The melting point for a crystalline solid is also sharp. And in crystalline, they may be metallic or non-metallic crystals. So, for example, we take copper, aluminium, magnesium, quartz, mica. All these are examples for crystalline solids. Now coming to the classification based on the arrangement of atoms. We have single crystal and polycrystalline. So we will first see what is single crystal. Now, if the entire crystalline material consists of only one crystal, then we call it as single crystal. Let us look at this figure 2a. If you see the arrangement of atoms here, all of them are arranged in a regular fashion and it is only a single crystal. So we call it as single crystal. Example, we have quartz and gemstones. They are all single crystalline. Now coming to polycrystalline. Poly means many. So in a polycrystalline substance or a material, we have many small crystals which are separated by well-defined boundaries. So now if you see the figure 2b, this is polycrystalline. Polycrystalline means there are a number of crystals. Now if you see, the arrangement in this region is periodic. If you see here, this is one more and this is one more crystal. Like that, we have many crystals that are arranged. So we call it as, these are the boundaries. So we call this as polycrystalline. So the basic difference here is, in single, it is only a single crystal where there is regular periodic arrangement of atoms. And if you see, in polycrystalline, there are many crystals which are separated by fine boundaries. Now coming to single crystal, X-ray diffraction studies have shown that atoms in crystalline solids are arranged in regular periodic pattern in 3 dimensions, and the arrangement of atoms is in specific relation to each other. That is what we call it as order. And in crystals, the order exists in the immediate neighborhood of an atom as well as over large distances corresponding to several layers of atoms. When we see here in 3 dimensions, along the different layers also, they are arranged in a orderly manner. That is why we call it as single crystal. Now, when the crystal is broken, it cleaves along a certain preferred directions. Wherever that is broken, it is broken along a preferred direction, and the same substance may crystallize under different conditions of crystal growth to form different geometrical shapes. They may form different shapes, but the angles between the faces are always constant for different shapes. That is what we call it as law of constancy of angles. The angles remain constant. Now in single crystal, the physical properties may vary with the direction. So whenever the properties are varying with the direction, we call them as anisotropic substances. So for a single crystal, we call it as anisotropic because the physical properties are varying with direction. We have already seen the examples: quartz, diamond, rock salt. All these are examples of solids that occur as single crystals. Now coming to polycrystalline, they consist of fine grains having a size of 10 power 3 to 10 power 4 angstrom. And 1 angstrom here is 10 power minus 10 meter. So the size of these grains is 10 power 3 to 10 power 4 into 10 power minus 10 meter, and they are separated by well-defined boundaries but oriented in different directions. We have seen in the figure, if you see this grain, it is oriented in this direction, and here the arrangement is in a different direction. The direction is like this. So, since the grains are oriented randomly, a polycrystalline substance is isotropic. We call it as isotropic, and the physical properties do not vary. So, in case of single crystal, we have seen the properties vary and we call it as an isotropic. Whereas in polycrystalline, the physical properties do not vary, so we call it as isotropic. And majority of the natural solids have polycrystalline structure. And the best examples are metals. When we take metals, they are all polycrystalline in structure. Now we are going to see one more classification, that is depending on the nature of bond. Depending on the nature of bond, we are going to classify them, because the atoms are bound to each other by electrostatic forces of attraction, and depending upon the nature of the bond between the neighboring atoms, they are classified as metallic crystals, covalent crystals, and ionic crystals. Now, in metallic crystals, the electrons are very loosely bound to the nucleus. So, whenever we see a metal, the electrons that are revolving round the nucleus, they are very loosely bound to the nucleus. But in covalent crystals, the interatomic forces, interatomic means the forces between the atoms which are there in the neighborhood, are directional, and the electrons are shared. So, like we see, if we have an atom which is having 4 electrons, if it has to form a bond with the neighboring, these 2 electrons may be shared by both the atoms. We have X and we have Y. This electron belongs to Y atom and this electron belongs to X atom. But these 2 electrons will be shared by both these atoms. Then we call it as covalent crystal. The third one is ionic crystal. So, in ionic crystal, the electrons are transferred from cation to anion. So, when we see cation is positively charged and anion is negatively charged. So, what happens here is there is transfer of electrons from cation to anion. Then we call them as ionic crystals. And the interatomic forces in these type of ionic crystals are non-directional. Now, when it comes to the periodicity of the atomic arrangement, R, the vector R is denoted by AX plus AY plus CZ. If we have to denote the position vector R, it is given by AX plus BY plus CZ, where X, Y and Z are the unit vectors along the X, Y, Z directions, and this is the condition for crystallinity. So, wherever there is periodicity, so we call it is a crystalline substance. Now, let us just summarize whatever we have discussed now. We have discussed about crystalline and amorphous solids, and we are just going to compare and contrast their properties. So, when it comes to crystalline, they are long range order arrangement of atoms. So, along a long range, these atoms have an orderly arrangement. And in amorphous, it is short range and the arrangement is random, we have seen. So, these are the key words. For amorphous, we say it is random arrangement of atoms, and for crystalline, it is orderly arrangement. So, these are the 2 keywords for crystalline and amorphous substances. And for crystalline, they have a definite shape, whereas for amorphous, the shape is irregular. And for crystalline, they are anisotropic. When do we say it is anisotropic? If the properties are varying, we call it as anisotropic, and they are isotropic like liquids. And here they are true solids. A solid means it is a solid, but amorphous solids, we call them as solids, but they are pseudo solids. Or we also have supercooled liquids. And crystalline substances have a definite heat of fusion, whereas here the heat of fusion is not definite, like we have seen for melting point also. The next one we are going to see about melting. They have a sharp melting point, and here it will vary a range. It is not sharp. In amorphous substances, the melting point is not sharp. There is a particular range at which it melts. So when we see this heat of fusion and also the melting points are fixed and sharp for crystalline solids, whereas it is not definite for amorphous solids. And if you see the examples, sodium chloride, diamond are examples for crystalline, and rubber, glass, plastic, all these are examples for amorphous solids. Now coming to lattice points. So what are lattice points? Whenever we talk about a crystal structure, we talk in terms of lattice points. So first we'll try to understand what these lattice points are. So a regular periodic arrangement of atoms is the most important feature of crystals. So till now we have seen whenever we are having a crystal, there is periodic arrangement of atoms. And whenever you see an atoms in a substance, that forms the structure. So the actual arrangement of atoms, we call it as structure. Suppose the atoms or cluster of atoms in a crystal are represented by points that correspond to their mean position. Suppose I have an atom here, and this atom will be represented by a point at its mean position. So like that, wherever the atoms are there, if these atoms are represented by points, it can be an atom or a cluster of atoms, then we call them as lattice points. So we obtain a regular distribution of points in space. Wherever there is an atom, we are showing it with the help of a point, which we call it as lattice point or lattice site. Now, if you have to define what a lattice point is, the simplest definition for lattice point is it denotes the position of atoms or molecules in a crystal. Now, you take the example of this crystal here. There are atoms at these positions, and the positions of the atoms are denoted by points, and we call them as lattice points. So, lattice points always denotes the position of atoms or molecules. Molecules are group of atoms in a crystal. Now coming to space lattice. What is a space lattice? A three-dimensional network of regularly arranged points, we call it as space lattice. Whenever we have this arrangement of points taken in 3 dimensions, we call it as space lattice. And whenever we say a point is dimensionless and shapeless. So point is just a point. Okay. So lattice is merely an imaginary geometrical framework. Means whenever we have to build a structure, so we need to know the points where the atoms are. So to understand different structures, crystal structures, it is easy to talk in terms of lattice points. So whenever we say lattice, it is only an imaginary framework. So a regular and periodic arrangement of infinite number of points in 3 dimensions we are calling as space lattice, and every point is identical, has identical environment as that of every other point. So whatever point you take here, so this will have an identical environment. All the other atoms are equispaced from this point, and when you take any atom, the environment is identical. And how we get the space lattice is by successive translations of initial points. You take a point and you will translate, means you will be measuring at the same distance and you will find another lattice point. So, space lattice is simply the skeleton upon which a crystal structure is built. How we are going to build a crystal structure? Wherever there is a lattice point, we are going to place an atom and then we get the crystal structure. That is how the study of crystal structures will become simpler. Suppose if 2 substances are having the same lattice. So, if you have to have, say, sodium, you will be placing all sodium atoms at those positions in that lattice. So we will get NaCl. Suppose we want potassium, KCl structure. So we will be placing the potassium atoms at that particular point. So the study of the structure becomes simpler when we are understanding this skeleton, that is the lattice structure. Now we will try to understand the relationship between a lattice and a basis. A crystal is a regular and periodic arrangement of atoms or molecules. This we have already discussed, and in three-dimensional space we are talking about. So how do we get a crystal? So we have a lattice. A lattice is nothing but the positions of atoms, if they are denoted by points, and in 3 dimensions we are calling it as space lattice, and the space lattice plus basis gives us the crystal structure. Now I will just explain it in lay terms without talking about any type of atoms. If you see here, we are seeing a flower here. I'll take this as a basis. And if I have a lattice structure which is like this, these are the lattice points we have taken in the space lattice. Now, how do we get the structure here is by placing this at each point. This will go to each point. So, when this same basis is placed at each point in the lattice, you get the crystal structure. So, what we get in the crystal structure is a group of flowers which are arranged in a regular fashion. So, what we have seen here is a lattice plus basis gives us the crystal structure. Now, in simple crystals such as copper, silver, gold, iron, so the basis is a single atom. So, whenever we are talking about this lattice and basis, the basis can be a single atom or it can be a group of atoms. So, often the basis consists of a few atoms. Now, we'll see the example for that. So, now what is this basis? A basis is nothing but a repeating unit assembly. And this assembly can be a simple atom, a single atom, or it can be a molecule, or an ion, or a radical. So, this assembly which is located at each point or the lattice point, we call it as basis. So, what is a basis? It is a repeating unit that is placed at each lattice point. And basis is an assembly of atoms identical in composition, arrangement and orientation. So, whenever we are talking about basis, this basis has to be identical atoms. Now, you see, we will see here, this is the lattice structure and a basis consists of two atoms. So, this is one and this is one. So, how do we get the crystal structure here? By placing this basis at each lattice point. At each lattice point, we are going to place this basis. Then we get the crystal structure. So, this is one basis. At this lattice point, this is another basis. So, like that, we keep on placing the basis at each lattice point. We get the crystal structure. So, this is the meaning of lattice plus basis gives the crystal structure. Now, let us look at what a unit cell is. So, unit cell is the smallest geometric volume. It is the smallest geometric volume which contains one or more atoms arranged in 3 dimensions. Now, till now we have been looking at this figure, which is a crystal lattice. So, crystal lattice is what? These are the lattice points which are arranged in regular fashion. Now, if we are taking a basic structure or the basic geometricals or the smallest geometric volume, I can say this is the smallest volume we have here. This, when it is repeated, you will get the crystal structure. So, what we are going to call it is like a fundamental building block. So when I keep this cell outside, so this is a unit cell. So a crystal structure consists of many such unit cells placed one after the other. So crystal is built up by translational repetition of unit cell. So these repetition of unit cells will give us the crystal structure. Now coming to lattice parameters. So what are lattice parameters? The lines that are drawn parallel. Lines drawn parallel to the lines of intersection of any three faces. So when we are talking about the faces here, so this is one face, I can say, along the x-axis, another face along the y-axis, and another one is a z-axis. So the lines that are drawn parallel to the lines of intersection of any three faces of a unit cell which do not lie in the same plane, we call them as crystallographic axis. So you can see here, this is one axis. This lies between this plane and this plane. And here, this is the axis y, which is separating this and this plane. And this is the So these axes x, y and z, we are calling them as crystallographic axis. They are nothing but like axis we consider in a three-dimensional object x, y and z axis. But here we are calling, because we are taking it in a crystal, we are calling them as crystallographic axis. Now, the distance between any two successive lattice points along any three directions is called as lattice constant. So what is a lattice constant here? It is the distance between any two successive lattice points. Now I will first consider along the x-axis or the x direction. If I am considering this direction, this is one lattice point and this is the next nearest, or we call it as a successive lattice point. The distance between these two successive points, we are calling it as A along the x-axis. So A is a lattice constant. And now when we take along the y-axis, this is the distance. B is the distance between the two atoms, successive atoms along the y-axis. So we call it as B. B is a lattice constant. And along z-axis, if you see, the C here is the distance between the two atoms. C is the distance. So the intercepts, we call them as intercepts A, B and C, define the dimensions of unit cell. Now when I am talking about unit cell, so the parameters or the lattice constants along the x, y and z directions are taken as A, B and C, and we also call them as primitives or intercepts along the axis. Now coming to interfacial angles. What are interfacial angles? The angles between the three crystallographic axes. We have seen about the crystallographic axis x, y and z. And the angles between these three axes we call them as interfacial angles. And these angles are represented by alpha, beta and gamma. So how we are going to represent them? There is a particular convention we use to denote these angles, interfacial angles. So now we see here, this is x-axis where we have taken the lattice constant as A between two atoms, and along the y we have taken it as B, and along the z-axis we have taken it as C. So A, B, C are the lattice constants along the three directions. Now the angle opposite to A is alpha. So this is the angle between y and z-axis. How do we remember? Opposite to A is alpha and opposite to B is beta. This is the interfacial angle B. So angle B will be between x-axis and z-axis. So between z and x you have beta. And the one opposite to C is gamma. This is the convention we are going to use. So gamma will be the angle between the axis x and y. So angle between x and y, we call it as gamma. Now these parameters, the primitives A, B, C, which we call them as lattice constant, and the interfacial angles alpha, beta, gamma, they form the basic lattice parameters because they determine the form and the actual size of unit cell, and that is how we have a space lattice. In 3 dimensions, when we see, suppose there may be a case where A is equal to B is equal to C. So A is equal to B is equal to C means in all the three directions they are arranged at same distance. So this is in case of a simple cube, we say all the sides are the same, then it can be A is equal to B is equal to C. So depending upon these faces and also the angles alpha, beta and gamma, if they are equal, we'll write them as alpha is equal to beta is equal to gamma. And there may be cases where A may be equal to B but not equal to C. So depending on these parameters, we are going to classify the crystals into 7 different types, which we'll be discussing later. So we'll be discussing about the lattice structures, 7 lattice structures and the Bravais lattices maybe in the next lecture. For any clarification regarding the topics we have discussed, you can refer to books by Dr. K. Vijay Kumar and Dr. S. Chandralingam, Modern Engineering Physics. And you can also refer to textbook of Engineering Physics by Dr. M. N. Avadhanlu and P.G. Ksirsagar. So thank you and see you again in my next lecture.
Like, share and subscribe. Hit the bell icon for more updates.